Welcome back. In the last few videos, we looked at renormalization group equations for a few theories, but we stayed in very simple cases. You might have noticed that we looked at lambda phi 4 and QED in the case where they were massless, right? But not only that, we also avoided higher dimensional operators, right? We focused only on those couplings which were dimensionless in 4 dimensions, right? And for that reason, we also stuck to 4 dimensions. Now we want to generalize that method, right? We want to be able to go outside 4 dimensions and also attack Wilson coefficients that have dimensions, right? Either positive in the case of mass operators, right? So we can go to massive theories, or inverse powers of mass, which are these non-renormalizable operators or higher dimensional operators, which mean the same, right? And of course that depends on the number of dimensions, right? The first step in that direction is to take a look at what we call local operators, right? We want to know how to do these renormalization and write renormalization group equations, right, for these local operators, right? And what are the local operators, right? In principle, it's a very simple definition, right? They are operators composed of the fields in my Lagrangian. So you can think of phi 4 as a local operator, and the local part comes from the fact that all these 4 fields are calculated at the same space-time points, right? But then the question is, in which context will we be interested? Because we know these operators all appear in our Lagrangian. If our Lagrangian is local, that means all these operators appearing in the Lagrangian are local operators. But I want to talk about these guys in a more broad context, even when these operators are not appearing in the Lagrangian, right? In which case we usually call them external operators. So we have seen a few examples of that already, right? So the first, let's call that case 1, right? So the first situation in which we could be interested in local operators is when we have these external local operators, and we have seen a few examples already in this course and even in quantum field theory 1, right? And one particularly important example is when we think of an electron being scattered by the external electric field or magnetic field, right? So you could write that in terms of a one-to-one scattering, right? You have some electron that starts with momentum p, finishes with momentum p prime, right? And there's some scattering matrix here, which is created by some external field, right? So this is a one-to-one scattering by some external field. One way of calculating this, right, is doing the perturbation, the perturbative integral, right, of this thing right here. So the electric field, right, the A mu field, since it's an external classical field, it goes out of this matrix element, right? This is the coupling, right? And you end up calculating only this matrix element between P and P prime of the current, right? What stays here is some psi bar gamma mu psi operator, right? This is just J, what we call J mu. So you see, in this case, I'm not quantizing the electromagnetic field. It's just a classical field. It has no dynamic in the sense that I'm not figuring out the effect of these electrons on that field. It's set from the start. It could be dependent on time, but all these dependencies are externally set. I'm not using any equation of movement to calculate A based on what's happening with the electron. It's just an external effect. And my electrons are being treated as quantum particles, and I will contract these operators inside J mu with P and P prime, right? If I'm treating that this in this way, right, you see that the what I will calculate in a quantum field theory is just the expected value of J mu, right, between these initial and final states. And J mu is not appearing in the Lagrangian. In fact, my Lagrangian is just the Dirac Lagrangian, right? Just a Lagrangian for free fermions, right? In which I'll get the propagators that appear when I contract this guy with the external states, right? So this guy will be calculated in this way, right? I'll take this J mu of x, right, to be just some vacuum expectation value, because I can turn these initial and final states as some operator acting on the vacuum. So I have the time ordered product of J mu x, psi x1, psi bar of x2, right? And these are the operators, right, that create the initial and final states, but I'll get contractions between them and J mu in order to calculate these. So I'm calculating the expected value of an operator, a local operator, times the fields, but that operator does not appear in the Lagrangian, does not even satisfy the symmetries of the Lagrangian, right? J mu is not Lorentz invariant by itself. So I'm calculating some expectation value of a Lorentz vector, right? Which is possible if you have some external effect, right? Which is breaking explicitly the Lorentz invariant, right? So just think of a external field, right? And that's one case where you can be interested in local operators. I might want to know how this guy runs as I include loops in this theory, right? Suppose there are other interactions between those guys, right? There's two ways we can indicate. There's a little trick we have to be mindful of here, is that since this local operator is connected to some external effect, there's no momentum conservation in the vertex at x, right? There's some external momentum going in. Of course, it's being exchanged with the external electromagnetic field. And there's two ways we can indicate that with Feynman diagrams. One way would be to draw my Feynman diagram like this, right? So I have some vertex here, right? And sometimes you can indicate this external field here by a wiggly line and something that reminds you of a source, right? And then, of course, there's when you do the Fourier transform of all these three guys, there'll be a momentum associated with each, right? So there's a external momentum here, right? And of course, it needs to be like that because that electron is being scattered. So it needs to exchange momentum with some external source. This is clear, but you need to be careful not to be confused by this wiggly line here. Otherwise, you think you need to include a photon propagator somewhere here, and there is no photon propagator in this calculation, right? I'm not even quantizing the electromagnetic field, right? Another way of indicating that is just to have this part here without the fake photon propagator, and indicates that you are injecting momentum on this effect, right? On this, let me color that green, right? Where the local operator is acting. So this local operator is capable of injecting momentum every time it is this external connected to external effect. That's when we call this an external local operator. And I'll use this one for the rest of the video, but it's important to not be confused by this vertex that is not conserving momentum, right? I'm just inserting momentum here because the local operator is connected to some external effect. right? A second case where we could be interested in local operators is when we integrate something out in the spirit of the Wilson approach to renormalization, right? So imagine you have a theory when you have the following interaction between fermionic fields and some vector field, a massive vector field, right? Let me write the interaction. And this is just not some ad hoc interaction. It's actually inspired by the electroweak interaction with quarks or leptons, right? It's exactly this one. So now I'm taking this W boson here. Imagine it has a mass, right? And that mass is quite high, right? You can say this guy is a massive vector boson. How is that possible? You have to look into spontaneous symmetry breaking, which is beyond the scope of our course, but just accept that it's possible to have a massive spin 1 boson, and the mass of this guy is MW, right? That means that the propagator for this guy is a propagator for a massive gauge boson, will be just I g mu minus I g mu q square minus w square plus I epsilon in my favorite gauge, right? And then there's a scattering possible with that interaction, right? It's very easy to draw a scattering where the fermions exchange a W. Let me put that here, right? So the Feynman rule for this vertex will involve g over square root of 2 times this complicated Dirac matrix structure, but the diagram is pretty simple. It's just this W being exchanged in some channel. Here I'm drawing the S channel, but it doesn't matter, right? We could choose any different direction. Let's just put some momenta here in case we need it. P2, I'll call Q the momentum of the W. So now this wiggly line is not the photon, it's some massive guy, right? And I have P4 and P3 here, right? The point here is, imagine I'm doing that same approach I did when we were doing the Wilson renormalization. So I can take low energy modes of my theory, high energy modes of my theory, and integrate those guys out so that only the guys created by these are present in initial and final states, and I can actually figure out that part of all my diagrams, and that generates operators that only involve the guys I didn't integrate out, right? I can do the same even for different fields, right? If the mass of the W is high compared to all other scales in my theory, suppose the mass of the fermions is small compared to MW, and also the momentum, right? All these momenta, P1, P2, P3, and P4, are all much smaller than MW. That means Q will also be much smaller than MW, right? And I could imagine doing my theory at a scale which is low, right, compared to the mass of this W. Now I don't even have to divide the field MW into regions, right? I don't have to take some W and W hat and integrate only parts of some modes for this field. If the energy, say MW is here, right? And I'm doing my calculations or my measurements at a scale Q square much smaller than MW square here, right? Then I can integrate W out completely, no modes, because there's a minimum, right? A minimum energy for the excitations of this guy since it has a mass, right? I can be in a region where W does not appear at all, only inside in the virtual states or loops, right? And in that case, I can exchange this interaction, which leaves here, right? Where I start producing MEW, I start producing the W, I start to see this propagator going on shell around here, I can go to a region where this guy is not present at all, right? And in that region, I can approximate this propagator, right? If Q square is small compared to MW, right? I can approximate this thing by disregarding Q square over here, right? In other words, any matrix element, in this case, I'm doing the same out integration I did for phi hat, but in this case, I don't even need to go to loops, right? I took loops of phi hat and calculated those loops. But since W contributes to this diagram at 3 level, I can do the integration out of at 3 level now, right? So a diagram like this, right, will be given by, schematically speaking, right? I have 2 different points here. At this point on the left, I have the action of this operator, psi bar W psi. On the point on the right here, I have again psi bar W psi, acting calculated at a different point, right? And this diagram is given by the contraction. I have a propagator from this point to this one for the W, right? This is proportional to G over square root of 2 on the left side. Of course, there's some Dirac matrices that I'll bring back later, right? I have the propagator in the middle, right? This is very schematic. I'm ignoring all powers of all powers of I, all Dirac matrices and so on, right? But this is the propagator, and I have another power of the coupling on the right for these 2 vertices, right? And once I ignore Q square here, this all just becomes a constant, right? And this goes to something that looks like a matrix element that now only involves these guys, right? But now you can see that the only dependence I had on Q square was coming from this propagator. If I'm ignoring Q square here, that means that the Fourier transform of this to the position space will be a Dirac delta, and that means these 4 fields will have to be calculated at the same point, right? Here they have 2 different points because I have a dependency on Q square. On this side, they'll be all calculated on the same point, right? Which makes this a local operator. And the coefficient here will be given by this if I take Q square to 0, right? So we'll have in front, right, some G square over 2mw square. And of course, this G min u will contract, will make so that the Dirac matrices that are here and here have a full contraction, right? Which was happening before anyway. So I'm exchanging now. What's happening here is that I'm exchanging these interaction at 2 distinct points for a local one that acts only at one point and involves 4 fermions, right? This is the story behind the Fermi interaction, right, between 4 fermions, right? But what we managed to do here is find the strength of this interaction from some ultraviolet theory that we know, right? So this is an effective theory with a coupling fixed by some higher scale theory that I know. This process is called matching, right? I'm just matching my low energy effective theory to some UV theory that I know details of, right? This is not always possible. Sometimes, in fact, historically, this very interaction was discovered in this direction, right? People first noticed that weak decays could be described by this 4 fermion interaction, which was not renormalizable, right? As we have said, that's not a problem if you have some suppressing scale, and the suppressing scale here is powers of MW, right? You can see that if I try to use the same interaction to build a 6 fermion interaction, I'll have an even higher power of MW, right? Some MW to the 4th or something. So there's no problem with this non-renormalizable interaction. But eventually, as you go up in energy, you discover that this is being generated by a renormalizable interaction, which is the W exchange, right? But you could, and in fact is much more smarter at low energies to work with this effective theory instead of this one, right? This is the most correct one, but at low energies, this is much simpler, right? And you could calculate the renormalization and the running of these local operator instead of working with W's that are really far below the energy where they could go on shell. So they are really very virtual in this case, and it's just a waste of effort to be carrying their dynamics around, right? You can just collapse this all to a point and have a simpler theory, which is easier to work, right? And if you don't know the ultraviolet theory, this can be useful too, right? As it was, right? You could, in principle, find these again, right? Non-renormalizable theories that could be generated by some UV theory, but you don't know which UV theory it is. In that case, you have to measure this value at some point, right? That becomes your reference point, and you calculate how the theory runs away from it without knowing anything about the UV theory. All you need to know is really the local operator, and that's also a pretty important use case for figuring out the running of local operators. And in a similar way to what happened with the current here, I will end up calculating matrix elements that involve this operator, right? And the fields in the Lagrangian, something like this, right? Psi bar P2, psi P3, psi bar P4, right? But in this particular case, right, there's no external momentum being injected, right? So I'll just put a 0 here, right? Because in this case, there's no external anything to inject momenta. So it's a particular case. In some cases, these local operators can inject momentum in my matrix element, or in other cases, they don't, right? And a third usage case for these local operators, of course, is just convenience, right? You could have some phi-6 interaction in your theory, which when renormalized, will get some -6/2 powers of z, right? And instead of analyzing each running of each field separately, I could think of this as an operator, right? O6, and this thing as some Z6, right? And study the operator as a whole, just as a matter of convenience, right? I could find a Kalan-Zimanzik equation for this object instead of each of these fields separately, right? So again, you could just think of local operators for convenience, right? In any case, whatever is the case you're interested in, the thing is that we'll define some operator, right? And now we'll limit ourselves to scalar theories just to simplify, right? And this operator is now some product of scalar fields. So this is a product of phi's, right? To some power. You have phi to some power, and that's the operator we are interested in. And when we renormalize our theory, in the same way we did with couplings, right, we can just introduce some counter term of the form delta O times this operator. And this counter term right here, will be responsible to renormalize the contributions from this guy, right? And then you, when you do that, you can define some renormalized operator, which I'll call all m, to remember that this guy now depends, I could call this guy O0, right? That this guy now depends on the renormalization scale, because I renormalized it, right, by some, and this is the definition of this guy, by some field redefinition OZO, right? Which again, it could be just this product of disease of the fields, right? And this is a function of the renormalization scale, and it multiplies the bare local operator, right? So again, I'm doing everything I did for the field itself, but now for this product of fields, because I could be interested directly only on this particular combination of fields, right? I could be interested in how the conserved current runs, for instance, right? So now, if I want to calculate green functions, I'll come up with a notation that I'll indicate it like that, right? I can have a green function with some number of external legs, which I'll call n, and some number of local operators. In this case, I'll just put 1, right? So gn1 depends on p n momenta for the external legs, and you could have injection of momenta, of one momentum, by the local operator, right? In this case, it's just 1, so I just call that k, right? And this is defined by this product in momentum space. It's just the product of fields for the external legs, right, times this operator renormalized that injects k, right? So GNM would represent m insertions of this operator right here, right? And so if you write this function now, this is in terms of the renormalized fields, right? I could rewrite the same green function in terms of the bare fields. In that case, I would have a power of c to the n over 2, right? Minus n over 2. And that depends on m. For the free field part, right? So that would take care of all the field renormalization. So now I replace these guys by the bare fields. Okay? And one factor of z operator here, minus 1 of m, for the local operator, which now becomes the bare operator. Again, we have done this before, right? Comparing these two equations, right? I can figure out what happens if I do a slight shift on m, right? I take m to m plus delta m and get a differential equation for the green function, right? It's not, that's not hard to do. I won't do everything again, but we could follow the same procedure we did for the Kalan-Zimanzik equation, and you can probably even guess the answer, right? It will be very similar to what we had. So nothing changes in the part where you have the dependence on the renormalization scale. You have some beta function, and here I'm assuming there's only one coupling in this theory for now, right? One dimensionless coupling, because you'll see that this is very similar to a different coupling, right? And you have the usual thing that comes from the number of external legs, in this case n, and you have a gamma of lambda that depends on how these guys get renormalized, right? It's the field renormalization constant that is tied to this gamma. But now you have a new one, right? For the operator. I'll call that gamma operator, right? And in this case, the coefficient is 1 because I'm inserting this operator just once, right? And that gives me the Kalan-Zimanzik equation for this green function now in the presence of local operators, right? External or not. If they are external or not, all depends on this momentum here. I can set it to 0 and then there's no external momentum going in, right? The definition of this new anomalous dimension, now I can call it like that. This is the anomalous dimension of this operator, right? You can call it gamma function if you want, right? Is now given by the same definition we used before, right? Because this is all very analogous, right? This is just m over z del z operator del m, right? It's how this varies as I change the renormalization scale. And of course, another way of writing the same thing is just m del m of the log of z o of m, right? Same thing. And that's the definition of the gamma function now. And it's the same definition we used before for this guy, right? Just replace z by zo by z, right? Exactly the same one. Now, there's one delicate thing that you have to be careful of once you allow the theory to have more than one anomalous dimension, right? Is that sometimes operators have exactly the same quantum numbers, right? So just to give an example, right? Take this operator 1, think of QED, right? And take this guy, psi bar, gamma nu, del nu, gamma nu, del mu psi, right? And this one, operator 2 is just f mu lambda f mu lambda. These are all local operators that you could construct. And if you look at the quantum numbers of these guys, right, the total charge and Lorentz transformation properties and CP transformation, all the quantum numbers, right, are the same. And that means that when I start running, right, I start changing my scales, right, this guy will generate contributions to this operator and vice versa, right? You could have some diagrams that externally, if you look at the external legs, there are these operator, but the loops inside are receiving contributions from this one. That means that one contributes to the overall rescaling of the other. In that case, you have to be more careful and define something that looks like this, right? You just define an operator, the Baire operator, with some index I, right, will be given by a Z, which is now a matrix that mixes these two guys like that. So even if you start with two separate Baire operators, as you run, one will contribute to the other, right? And then you have to generalize this definition for the case where Z is a matrix, right? And it becomes something that looks like this. Right? Look at this definition. Now I have the inverse. Let me put the indexes outside. So I have Z minus 1 ik m del m, right? This is just this 1 over z here, right? And I'll have Z operator M K J, right? So that becomes more complicated situation. We won't do that in this course, but if you're curious, you can look at Peskin and Schroeder's book and chapter 18, right? Especially section 18.2. It has some practical applications in which this kind of thing appears, specifically for the weak interaction that I have just commented. But in order to do that, you would have to understand a lot more about the standard model, and we're not doing this in this course. So just keep in mind that this is a possible situation, but we'll limit ourselves for simpler cases where the local operator we're seeing is not mixing with any other local operator, right? In that case, we can obtain a gamma function for that operator, right? By choosing, right? The same way we did with the 5-4 theory and QED, we can choose the appropriate green function, right? And do some judicious counting of powers of the coupling, right? Just choose the good green function. We could isolate gamma inside the Kalan-Zimanzik equation and figure out gamma for a specific case. And let's do that for the green function we just defined, right? I can take n external legs and one insertion of the operator, right? Again, this is given by this product of operators. So have n external legs and one insertion of this operator renormalized at point M, right? And I can write this expansion. Remember, I'll have diagrams contributing to the vertex, including this thing is inside there, plus counter terms, times the external legs, right? Some product over propagators for the external legs. But then I can do this product and take only the terms that have only one insertion of loops, right? Like we did a few videos ago. In that case, what is left is just this, right? I won't have products of two bubbles like that, nor products of two counter terms, but I'll have the part that is equivalent to the vertex. So see now, I have a green function that has n external legs, one insertion of the local operator. So this blue dot here represents the local operator. I can have some momentum k going in through that operator, but really physical legs, right, particles, are just given by these n external fields. I have a counter term, which is the counterpart for the renormalization of the local operator, and this is given here, right? And then I have the part for the external legs. I don't have cross terms because they are all here, right? I'm ignoring the two loop contributions or more than one power of the counter terms, right? And for the external legs, of course, I have all loop contributions to legs concealed by the counter term for the legs. This is very similar to what we did to get the expression for gamma in general scalar theories a few videos ago, right? Using the same logic now, right, we know that the dependency on the renormalization scale will be only here and here, right? Once we set the condition so that this counter term conceals the infinities that are coming from here and here, and thus the renormalization, right? I know that these guys will become dependent on this renormalization scale, and that means that the derivatives in M on G will act only on these guys, right? And then at leading order, I can argue, I won't do everything again, that this dependence on M will have to be concealed by these guys, this guy only. Everything else is higher power, right? In the coupling constant, especially this term here, I can disregard at leading order, and then write that the gamma of the operator is given by m del m of minus this counter term plus n, because of the number of legs, over 2 times this counter term. Right? So this is very equivalent to some expressions we found before. And the important thing here, I don't know what this line is. Let me just put, this is dependent on lambda, of course, right? And this is the important thing, right? We have a clear way at leading order, right, to calculate gamma from these counter terms. So if we do the renormalization of this operator, and of course the normalization of the propagators for the theory, we'll know the value of gamma, right? So there's one useful case for us in which we can apply this formalism and are already set up what we need to later introduce masses in these theories, right? We're doing massless theories so far, is to look at the particular operator, which is phi square, right? We know this guy, if introduced in the Lagrangian, gives us a mass, right? But we can now introduce it as an external operator and perturbatively insert mass in these theories. This will be useful because then we have control over our RGE, right? So the logic here is, let's go back to lambda phi 4 now. So we have been dealing so far with lambda phi 4 in a massless case, right? And that means that I start with a Lagrangian where the bare mass is 0, but also all the corrections to this bare mass are also 0. That means that the loops in lambda phi 4 that introduce a mass will cancel exactly with the counter term. You have to be careful. Let me write it like that. The correction to the mass will be 0, and that means the counter term will be equal to the loop contributions to the mass, right? So I keep that being true, right? This is all 0. But now I'm calculating this external operator, right, that can even introduce some momentum. So this will effectively turn my theory, right? Any matrix element that I calculate in the presence of this, right, in the limit where I take this external momentum to some value, right, will have a mass. But this is not the pole mass, it's a running mass that I'm introducing this way, right? And that will allow me to study the running of these running masses. This is very similar to the MS or the MS bar scheme masses, right? It's not a pole mass at all. In that case, I can do something very similar to this. My diagram will look like this, right? I can look, for instance, to some matrix element with two external scalar fields with momentum Q and P, right? But in there, and I can pull out this part of the diagram here, I have one insertion of this particular operator, right? And that allows me to insert momentum K here, right? Diagrams like this are contained, right, are given by these matrix elements. So I have something for this external field P, something for this external line Q, and I'm inserting a phi square of k here, right? So again, I'm calculating a matrix element in the presence of some external operator phi square. This is a leading order, right? For these external legs, just I over p square. For this one, I over q square. And the Feynman rule for this guy is just 2, right? Because I'm not putting any constant in front, I'm just thinking of the operator for now, right? And now I can put some renormalization condition for this guy, right? If I don't want to, as you notice, I'm not. This does not depend on k, because I can impose that this is true, right, without corrections, because this would be true at leading order, but now I can think of what happens once I put loops everywhere here. But I can demand that this whole thing is equal to just what you would get at leading order at a particular point, right? So p square equals q square equals k square equals minus m square. So this becomes now a renormalization condition. So these loops can be complicated, could be infinite, could be anything, right? But at this particular scale, I have the same I have at 3 level, right? At just the leading order for this object, right? And this is a renormalization scale that will, renormalization condition that will fix the counter terms once I calculate this at one loop, right? At one loop, what is the first contribution to this, right? This will be, again, we are in a lambda phi 4, so I have a lambda phi 4 interaction. P and Q must be going in this lambda phi 4 vertex. So this is P, this is Q, right? Then I have a loop. That goes into this blue dot here, which is my local operator, right? And of course I have some momentum k going in here, which complicates my momentum conservation a bit, right? I have to give some name to the loop momentum going in, right? I'll call that one R, right? This is my integration variable. And that means on the left side here, I have R plus K. And that deals with momentum conservation completely, right? Now, I can write the Feynman rules for this diagram. This is I over P square, I over Q square. Now I have different momenta on each side of this loop, so there's no symmetry factor, right? I can do this integration in d dimensions because that's the regularization I'll use. Now my variable is R, 2 pi d here, I over R square, this momentum, and the other one is just I over K plus R square. So you see, I'm inserting this operator as an external operator, but I'm treating the theory as a massless one for now, right? So mass is 0. One thing that I'm not doing here anymore is to introduce, right? I'm doing dimensional regularization. So I could have introduced at this point a mu to the epsilon here to keep my, in fact, I forgot the coupling. Let me put the coupling here. This is minus I lambda, right? For lambda phi 4 here. I should have put a mu to the epsilon here to compensate and keep this guy dimensionless. But we know that if we're doing this scheme here, eventually this mu will be the log of mu, will conceal everywhere. So I'm not even putting that in just to remove at the end. That will keep things clean, and the price to pay is that sometimes we'll have log of dimensionful quantities like that. But it's implicit that you should have a mu square there, which I'm not putting in just to save us from writing stuff that will disappear at the end. In this scheme, it just goes away, right? Now we need to do this integral. It's the same tricks as always. I'm not doing that in detail, right? This is just these two guys, right? Times minus lambda over 4 pi square, gamma of 2 minus d over 2, in dimensional regularization, right? And delta of 2 minus d over 2, right? In this case, the delta will be a function of all these momenta there, but for when you impose this condition, and that's what mattered to us, you can check, calculate delta and check that delta will be just m squared, right? If I impose all of that. Right? And so this loop needs to be concealed by the counter term, right? So when I introduce phi square, I also need to introduce some delta phi 2 counter term, right? And this guy gives me a Feynman diagram. Let me copy my symbol for counter term here. This introduces some Feynman rule of this sort, right? And this is given by these two external legs. That's the rule for this guy, right? Times 2 delta phi 2. Just because I'm not putting factors like that, right? I didn't put it for phi square, so I'm not putting it this factor of 2 for the delta phi square, right? And that, if I take that condition, that renormalization condition, I need to add this loop for substituting delta for m squared and p squared and q squared by m squared, right? And add this loop to this guy and make sure this condition is satisfied. And that will tell me that delta phi squared is equal to lambda over 2 times 4 pi squared times this thing, right? Gamma of 2 minus d over 2 m squared to the power 2 minus d over 2. So I'm doing this really quickly because it's again a very boring repetition of everything we did before, right? So if you're really curious, you can do it yourself, right? But there's no special tricks here. It's just the usual renormalization. And since I'm only really interested in the divergent part, because that's the part that depends on the renormalization scale, I can do this very quickly, right? And don't worry about anything else. Now, if I want to get the dependency on M, right, I want to use this specific formula here to get the gamma for this operator, right? We know that in lambda phi 4, delta z is 0 at leading order, so we don't have to worry about delta z. I just have to worry about this delta phi square which I got here. And we know that this, if you take the number of dimensions close to 4, this is just lambda over 2 4 pi square, right? Times minus log of m square plus other stuff that does not depend on m square, including the 2 over epsilon, right? This is here. And this is the part where the derivative acts on. So if I copy that formula, this one, and use it here. Now I'm talking about the operator specifically is my phi 2, right? So here I put phi 2. Delta z is 0 at leading order for lambda phi 4. We have seen this more than once already. So I just have to take the derivative of this, right? And that's pretty easy. I'll have a minus here. The derivative is this, just minus 2 over m. So, and the m goes away. So that's just lambda over 16 pi squared, which is this one, right? This 2 was concealed by the derivative here. The minus is, this all goes away because the derivative of this part is minus 2 over m, right? Which conceals this m, this factor 2, and that minus. So you just have lambda over 16 pi squared. So we calculated the anomalous dimension of this operator now, right? Which will be useful in order to discuss the running of running masses. Remember, every time I'm talking about a running of a mass, you should think of it more as a coupling, like because running mass is not the pole mass. But the point is that you can, as we have seen in the video where I mentioned the MS scheme, you can later relate the running mass to the physical mass because they coincide at some point, right? As I go through my scales, I can run the running mass all the way to the pole mass, if there is a pole mass for the particle. So we'll be using that pretty soon to study the running of masses, right? But that's for the next video. This is it for this one. Thank you.